All right, so hello students. Welcome to our first online lecture, our flipped classroom that I'm trying out. Today is just a review day. This lecture should be review. There is a couple concepts that will likely be new, but for the most part it's just review and catch up. So the first part of this class, we're going to review some concepts so that we're going to review them kind of quickly. I'm not going to cover them as in depth as some classes would, because I want us to get right to the statistics, the tests, because that's what we need to know how to do for our chosen profession. So this is just a review. Some of it's new, but most of it's review. A lot of it's review about experimental methods and design. Some of it's what I believe is common sense, like this slide right here. Now, the statistics we use in this course attempt to make conclusions about populations from samples. A population equals all the people in an entire group. Let's say, like in this picture right here, all mountain climbers in Denver. Now, a sample, what you see there, is just a subset of these individuals. So, let's say I was interested in all mountain climbers in Denver's fear response. This is my population. However, it's impossible for me to interview all these folks. So I have to interview a subset. That's the sample I just took. From the sample, we will infer conclusions about the population. So what this means is if you have the entire population, you do not need to use the complicated statistics that we are going to learn in this class, because these statistics we use are trying to infer population parameters from sample parameters, from samples, right? We're trying to infer the population, what's going on there, from the samples we take. But it's a very simple idea. Sample is a subset of the population. Now, before we get too far into what statistics are, there's two classes of statistics that are worth discussing. Descriptive statistics are statistics that describe your sample directly, require basic calculations like calculating a mean, and the only way to really be wrong in a descriptive statistic is to do your calculations incorrectly. Now, you can probably see a trend here, but inferential statistics, right, infer population parameters from sample data, particularly from descriptive statistics from the sample, and are the foundation of the statistics we use in this course. These statistics do require complex math theory and assumptions that are not simple. We will not be talking about most of these theories and assumptions because that's the work of statisticians. In general, these statistics are anything that involves a p-value. So inferential statistics, the real conclusion of an inferential statistic is the p-value. So that's really how we're inferring about the population from the samples with the p-value. So that's the foundation of inferential statistics. It's p-values. And interestingly, even if you do your statistics 100% correctly, your inferential statistics 100% correctly, you can still make an incorrect conclusion. For example, if your p-value is 0.01 and you make the conclusion that your control group is different from your experimental group, there's a 1% chance that your conclusion is wrong, even if all your math's correct. Don't worry about that too much. I just want you to realize that inferential statistics are probabilistic. Even when we do them correctly, we may have an incorrect answer, and that's important to understand before we move on. So in order to do any statistics, we must turn our observations into numbers. If it cannot be converted into numbers, then you can't use it in psychological science. Not really, not with the statistics we use. So take, for example, gender. In order to run statistics on this variable, I have to assign numbers to each different gender. right? In this case, these numbers do not mean anything about quantity of gender. They simply tell me that a participant identified in a very specific way, right? So it's important to realize that we have to turn all our observations into numbers. And those are what we call statistical variables. When you take an observation and turn it into numbers, that's a statistical variable. If you can't turn it into a statistical variable, you're not going to be able to run the statistics on it that we need in psychology to make the conclusions that we want to make. So step number 1 in statistics is convert your observations into numbers. Super simple. Now, in terms of statistical variables, there are 2 classes. I'm going to start on the right with continuous variables because you're most familiar with them. Continuous variables are simply numbers that hold the rules of numbers that we have been teaching you your entire life. Now, I have an example in there of free throws, number of free throws that a participant makes in 60 seconds. This is actually something that is used in psychology to examine performance, response to stress, motivation, all sorts of things. Now, for this example, 0 equals the absence of free throws made, right? The distance or interval between 1 and 2 free throws is the same as the interval between 100 and 101 free throws. Just 1, right? When the numbers in a variable are equally spaced, the difference between 1 and 2 is the same as the difference between 7 and 8. It's the same as the difference between 100 and 101. We have a continuous variable. All right? If 0 equals the absence of that variable, we have a ratio variable. So in the example of free throws, 0 free throws means you made 0 free throws. No big deal, right? So in that case, that's a ratio measure. That's a ratio variable. If 0 does not equal the absence, we have an interval variable. Take that 1 to 7, how happy are you question. That's an interval measure. Now I'm going to go to the left side of the slide. Discrete variables have numbers. As mentioned earlier, right? Like all statistical variables must be turned into numbers in order for us to use them in psychology. However, the difference between discrete and continuous is that discrete variables, the numbers simply represent different categories. They do not maintain a consistent interval. So in a discrete variable, the difference between 1 and 2 is not equal to the difference between 4 and 5. Because in these variables, we are simply using numbers to represent different groups because we have to in order to calculate statistics. Right? And in terms of discrete variables, none of them have that interval. That consistent 1 to 2 is the same difference as 4 to 5 and all that. Nominal, the difference between nominal and ordinal is quite simple. Nominal are just naming categories. Another, 1, 2, 3, 4, and 5 in my gender example before, the higher you go, it doesn't mean the more gender you have. It just means you're in a different category. 1s are different than 2s. 2s are different than 3s. 3s are different than 4s. 4s are different than 5s. There's no rhyme or reason to my numbering other than I needed to have it done in order to do my analysis, right? Like, that's a nominal variable when the differences are just names. Ordinal, on the other hand, sorry, excuse my little pause here. So ordinal, like the difference there is that increasing numbers equal increasing values on the construct. So take class year. First years have less credits than sophomores, who have less credits than juniors, who have less credits than seniors. However, while juniors have more credits than sophomores, this difference is not constant. Some juniors have one more credit than some sophomores, while other juniors have 30 credits more than some sophomores, right? Like, in that case, it's just order. We know that there's more credits. We don't know exactly how much. They're just kind of spaced out, right? So we got ratio and interval. Those are continuous numbers. Those are numbers where the interval is held constant across your entire variable, right? So, the difference between 1 and 2 is the same as the difference between 2 and 3, right? That makes it a continuous variable. If 0 is actually the absence of, then it's ratio. If 0 is not the absence of, it's interval. Discrete, on the other hand, you either have names, you have numbers assigned to names, like my gender example, or you have numbers that are ordered, but there is no interval there, like my class example. Now, I have a thought question for you. Is a 1 to 7 happiness rating an interval variable or an ordinal variable? Logically, I'm gonna say this. You can argue for both. You could assume that humans understand their feelings, and when they choose 7, they are 7 times as happy as when they choose 1. Or you could argue that they don't actually have that strong of a grasp of their own emotions or our own emotions, and these numbers simply represent more and less happiness, but the intervals and distances are not the same, right? That would make it an ordinal variable. While you are logically correct, it can be either an ordinal or an interval variable, our field consistently assumes these variables are interval measures for one simple reason. If we didn't, we couldn't run statistics on any of our Likert scale measures. So I do want you to know that while you can argue that a 1 to 7 scale is ordinal, in our field, we argue that it's interval because we have to. If we don't make the assumption that those variables are interval, we can't use them. Now, this is one that you should already know. What is an IV, independent variable, and what is a dependent variable? Now, I have this phrase called this causes that to help us remember that. Is causes that. Is causes that. Now, I'm saying it that way to help my memory. I know I sound ridiculous. I know it's hilarious. I know you're probably laughing at me right now, and that's fine. But I will never forget that I causes D, right? It, if you have to. The independent variable causes changes in the dependent variable, right? And so you just got to remember this. An experimental manipulation is always the independent variable, right? I do have a little note in here. I have a lot of students who get confused and they think something like they think one independent variable set, like a control group, a treatment group, 2 treatment groups, they think that's 3 independent variables. Let me put this in context, okay? If I was a neuroscientist and I had a control group where I gave my mice no drugs, I had a treatment group where I gave my mice 1,000 milligrams of drugs, and I had treatment 2 groups, another dose group where I gave them 2,000 milligrams of drugs, right? That is only one independent variable that has 3 levels. It's one independent variable, not 3. A lot of my students mess this up. You just got to remember this, right? In order for it to be a variable, it has to have more than one option, right? So it can vary. Now, in this specific case, we only have one independent variable here. I would call it dose response. 0 dose, 1 dose, and 2 doses, right? No big deal. And measures are mostly dependent variables, and I say mostly because that should really foreshadow the next slide. Don't get too caught up into it, but measures are mostly dependent variables. It's not the next slide, it's a few slides away. So, what makes a good manipulated variable? What makes a good independent variable? It's the same question. I use a little bit of a different notation than a lot of folks because the independent variable notation can be misleading for some folks. But, I'm going to call it a manipulated variable. We're going to know that I'm talking about an independent variable. Now, I want you to critique variables. I want you to be able to look at a study and be like, ooh, is this a good independent variable? And I want you to use these criteria. 1. Was the manipulation valid in that it made participants activate the psychological reality you were trying to manipulate? Let's say I was trying to manipulate stress by having you take a stats class. This is a valid manipulation for some. It creates stress for some. However, this is not valid for others, as being assigned to a stats class creates no stress for some lucky individuals. When you critique validity, you have to think about the alternate ways this manipulation will make participants feel. If in your opinion, it makes most participants feel the same way, it's a valid manipulation. Now, I would argue that the manipulation of being in a stats class is not a valid manipulation of stress because it won't affect most of my participants in the same way. That's my argument. And that's the argument you need to make for a valid manipulation. If you think the manipulation won't affect your participants in the same way, or a similar way, I'll say similar, same is exactly the same, that'll never happen, but similar way, then it's not valid. The second thing I want you to focus on was the manipulation reliable? That is, did your manipulation make the same person experience the same psychological reality? Let's take the stress of having participants take a stats class. While this may not be a valid manipulation of stress, as I said earlier, I would argue it's reliable. That is, it consistently creates a specific level of stress in your participants. Yes, some people experience no stress and some people experience high stress, but the important part is that those specific people will consistently experience the same amount of stress. Right? It's not like when you hear, I've got to take a stats class, your stress is going to vary based on what day you're told. I mean, a little bit, but not much, right? Reliably, your level of comfort with math and stats is going to determine your stress level to that manipulation, but you're going to consistently have that same level of stress to that same news. Reliability of the manipulated variable can only be examined by adding a measure. You apply the IV and you measure the DV. That is, you conduct an experiment. Then you examine the results. Then you redo the experiment again at a different time. Do you get the same result? If you keep getting the same result, you can assume that your manipulation is and was reliable, right? We have to replicate our work to see if our independent variable is reliable. And you'll see in the next slide, we're also seeing if our dependent variable is reliable. When we examine if our entire study is reliable, we then can assume that our manipulated variables, our independent variables, are reliable, and our measured variables are reliable as well. We'll get to that in the next slide. I'm going on to my third criteria, power. Power is the ability of an entire study to find a significant difference, if one exists in the population. Remember, it's inferential statistics. We're inferring about the population. You can increase the power of your study by making the differences between your experimental conditions, your experimental and control condition, drastically more different. However, in this case, low power is not always bad. If you purposely design a low power manipulation where the differences between the conditions are not that great and you still find a difference, then you can say something like, this effect is so strong, it even shows up in cases where stress is present but still very low. And you can look at my example there. Here's a low-powered condition, the experimental condition. You will have to give a speech to me in 25 minutes on statistics. Control condition, think about statistics for 25 minutes. I'm going to argue that this is lower power than my next manipulation. It's not a massively strong manipulation of stress. All I'm saying there is that give me a speech about stats in 25 minutes. It's kind of stressful, but it's not too stressful. Versus a control group, I want them thinking about stats. I want to have a good control group. That's an okay one, I'm just using an example here. But ultimately, like that is a lower powered manipulation than my next manipulation, where you will have to give a speech to all psych neuro professors in 5 minutes on statistics. The control condition is just think about statistics for 5 minutes. Now, when you think about power, in terms of your manipulation, you're asking, how different are my control and my experimental conditions? How different are my different conditions if you have more than one? How different are my conditions in my independent variable? Can I make them more different? Is this the most extreme version? Is it the least extreme version? What do I infer from this power? Now, in this case, low power is not necessarily quote unquote bad. Because if you find a difference with a low-powered manipulation, you're like, wow, this effect is really strong because even in this mild stressor, we still see the effect. So these are the 3 things to think about, right? A good manipulation is valid. It's creating the psychological state you want to create. It's reliable. It reliably consistently creates the same psychological state. Reliable and valid, it consistently creates the psychological state you want to create, right? That's putting them together. But, power depends on the situation. Let's say if you're reading a study and it reports no difference, but they had a weak manipulation. For you should be like, well, the conclusions are not trustworthy because the manipulation was too weak. Right? Like, you're like, ooh, they're saying they have no difference here, but they really had a bad, weak, low power. How can we conclude anything from that? That's where you would be at. Likewise, you can have too much power. If the manipulation is so strong that it rarely happens in the real world, like take my example here. When are you ever going to be asked to give a speech to all psych neuro professors with only 5 minutes of preparation? That's never going to happen in the real world. So in some ways, once you get to the higher powered situations, it's becoming less and less likely that that's going to happen in the real world, that kind of manipulation would actually matter in the real world. Nonetheless, with power, you got to think about, well, does it exist when there's low power? Does it exist when there's high power? What's the result that's being reported? But ultimately, a good manipulation is valid. You're creating the psychological state you want to create. It's reliable. You consistently create the same psychological state. And, you're thinking about the power of the manipulation. And you're thinking about what that means for your study. It's not as clean and crisp as validity and reliability. Now, measures also have validity, reliability, and power. Validity of your measure is basically the same idea. Are you measuring what you say you are measuring? Let's say we're measuring the stress response with the galvanic skin response, which is simply how much someone sweats, right? Are we measuring stress? We may be, right? We do know that the galvanic skin response is associated with like an increase in stress in the body. So we may be, but what if the room temperature is pretty high in our testing situation, and we're simply measuring differences in how one responds to hot temperatures? Right? In this case, we have a question. Are we measuring stress, or are we measuring something else like body regulation processes, body heat regulation? This is a case, what I'm doing here is questioning the validity of this measure, and this is the kind of thinking I want you to do, right? Even if it's a good measure, try to tear it apart. That's okay. Galvanic skin response is a good measure of stress, but also it's flexible. It's responsive to other aspects of our world. It's responsive to my body's tendency of regulating heat, right? Does that make it not valid? It very well may have. When we first started using the study, we didn't know until we gathered the data on it to show that it reliably was able to predict the stress response. Or, yes, and we'll get to reliability in a second, but is it valid? Is it a measure of stress? That's a great question. Again, reliability of a measure is a lot like reliability of a manipulation. When you measure the same person in the same state, you get the same result. We test the reliability of our measures with test-retest reliability. That is, we give our participants the measure at time 1 and then give it to them again at time 2. Then we see how highly correlated these measures are. In general, if that correlation is above zero point 0.6 or zero point 0.7, depends on who you talk to, we say we have good test, retest reliability. However, again, the better way to show reliability of your measure is to just replicate your entire experiment. This way you know that your manipulation consistently and reliably leads to the same experimental result. So for me, replication is the way to show reliability of your independent variable and your dependent variable. Remember, measured variables are dependent variables. Now, power of a measure is related to power of manipulation, but it's also different from the power of manipulation. Remember, power in general is the ability to find a significant difference when a difference exists in the population. On the measuring side, your DV has to be able to detect the smallest differences in the psychological state. That's how you increase power. So take sweat, right? These physiological responses are nice as they can detect the slightest changes in your stress level. We know that from past research, right? So in terms of stress, I'm gonna be able to detect even the slightest change by measuring your sweating response versus a 1 to 7 open response, open-ended questionnaire. Not open-ended, but Likert scale questionnaire, right? Like I'm going to have more power with your sweat than I am with your 1 to 7 scale, because you're not even aware of these changes in stress as they happen in your body, but your sweat glands are. And I think that's really cool and really important. When you think of the power of a measure, I think the best analogy is a microscope. On power 10, I can see some things like the outline of the cell, maybe the nucleus, but on power 10,000, I can see individual strands of DNA. Maybe I'm wrong in the power terms. Y'all neuroscientists can fix that for me, but in terms of power of your measure, think of it like a microscope. You want to be able to detect the slightest changes. If I have a more powerful microscope, I can detect changes not in only the size of the nucleus, but in the size of the DNA strand, right? Like I can detect the slightest changes in that cell versus when I have a power of 10, I can maybe see the nucleus. Maybe I could see a massive change if DNA just started freaking growing in there. And I know that doesn't happen, but I'm just using this as an example. I would be able to see that if there's like a tumor in the nucleus, I might be able to see that, but I wouldn't be able to see if there's a lot of DNA unraveling in that nucleus, right? I can when I have a higher powered microscope. Just like in terms of science and microscopes, we want to think about our measures. How do we make a more powerful microscope to measure stress? That's the main idea. So now you understand validity, reliability, and power. If not, come talk to me. But I want you to think about these things. I'm going to ask you to critique your own study in terms of validity, reliability, and power of your manipulation or your independent variable, and of your measure or your dependent variable. So those are the ways to start thinking about good studies, good designs, good manipulations. Now this one should definitely be a review, so I'm going to go through it quickly. Types of research: experiment and correlational. Now, an experiment is an experiment. There's a true experiment has at least one manipulated variable and one measured variable. Your independent variable equals your manipulated variable. Your dependent variable equals your measured variable. And you can use the word cause in this case. Now, for correlational designs, I'm going to talk about two. There's others, but I'm just going to talk about two right now. There's the quasi-experiment that confuses my students. Now, you have two measured variables, but one is categorical, like gender. And students see that as a true experiment, but it's not, because you did not manipulate gender. You did not assign people to different categories of gender. So it's not an experiment. It looks like an experiment. You use the same you'll see we use the same statistics to examine the quasi-experiment as we do the true experiment, but it's still a correlation. You cannot say cause. Be careful. Quasi-experiments look like a true experiment. The only way to know the difference is, did I randomly assign people to different conditions, right? To different conditions of my independent variable. Like, if you can't randomly assign people to gender, then guess what? It's a correlation, even if we use the same statistics, which we'll learn later. And then, of course, your correlation, two measured continuous variables, right? That's the difference between a correlation and quasi-experiment. There's just two measured continuous variables, two interval measures, two ratio measures. It doesn't really matter. It's just a correlation. The thing to watch out for is watch out for your quasi-experiment. Ask yourself, was the independent variable actually manipulated or was it measured? Now you can see why I use the words manipulated and measured, because I don't want you to be confused, right? Most independent all independent variables are manipulated, right? All dependent variables are measured, okay? But some independent variables like gender are measured too. So that's why I call them measured and manipulated variables. Now, I do know that a lot of my students know that correlation is not causation, but I need you to think like a scientist. Correlations are very important. Correlations in my own research were the only thing that allowed me to know a real world effect existed. My research is on racial bias and pain treatment, and there were years of hospital studies showing that one's race affected the quality of pain treatment they received. That's a correlation. And I'm bringing that up because it's important, right? That's a real world effect. That's where my research started, from a correlation. Then I converted my correlation to experiments to find out the causes of this horrible thing that I study. And I found that it was lack of empathy through experimental manipulations, right? But I'm a little over the phrase correlation is not causation. That's a high school statistical mindset. What's a better statement is, for every correlation, there's a cause to discover. Is it that X causes Y? Is it that Y causes X? Does Z cause both Y and X? Or does X cause Z, which in turn causes Y? Or does Y cause Z, which in turn causes X? Correlations tell us something important in the real world. They are not write-offs. They can't tell us cause, but they should lead us to do experiments to find those causes. Correlation is not causation, but for every correlation, there is a cause to discover. Now, within versus between, this should also be review. Between is very simple. You have different participants in the experimental and control conditions, right? Different participants in the different levels of your independent variable. I often just default to experimental and control because that's the foundation of the way we think about science. Now, within, you have the same participants in the experimental and control conditions. Very simple. I will just say it, within subjects designs, if you can use them, are better. So it controls for all possible individual differences. And in humans, this is very important. We have very unique and individual responses to stimuli, right? Like, if I want to reduce the error in my work and be able to increase the power of my study, the power to find a significant difference if one exists, right? Controlling all human differences, everything that we're different and special on, holding those constant across my study is pretty freaking important. I really that can be the difference between having the power to find a difference and not having the power to find a difference. So I love within subjects designs. They're more powerful, like I just said. They do have some downsides that you talked about last time. There's practice effects where I get better as I keep working at something. And there's carryover effects. A manipulation will taint, if I'm in, the control and experimental manipulation, I get the experimental manipulation first, that's going to taint my response to the control condition. For example, in my research, I told people to engage in empathy, or I told them to engage in their best treatment practices, right? Well, for me, when I did that, I was like, well, if I tell them about empathy in the first trial, sorry about that, my phone went off. If I tell them about empathy in the first trial, and then I ask them to join the control group where they're just trying to do their best, it's going to be really hard for them to ignore what I just taught them 10 seconds before, right? So there are carryover effects, there are practice effects. However, if you can, you should use within subjects designs statistically because it has more power, right? I know you know the downsides from the experimental, from like the experimental design side because you've already done that, you've already thought about it. But if you can, you should always use it within subjects design. And throughout my years of experience, I've actually solved a problem for most of my situations. I prefer within subjects designs, but for every study I design, right, every within subject study I design, I nest a between subject study inside of it. So I'm going to pull up my cursor here. So we have the first trial. Half your participants saw happy before sad, right? Happy. Let's just make it a silly experiment. You see a happy face or a sad face, and I rate how happy you are. That's it. We're just going to keep it simple. So half my participants right here on this line, they see a happy face and they rate how happy they are. Oh, tell them from the Midwest. I just said, oh. So they see how happy, they rate how happy they are. Then right after they saw this sad face and they rated how sad they personally were. Right? The same thing here. These participants, they saw the sad face first, right? Half my participants saw the sad face first, rated how happy they were. Then they saw the happy face and rated how happy they were. Right? We can see carryover and practice effects, maybe consistency, that sort of thing. We can see all the problems of the within subject study. But what I want you to notice is that trial 1 is a pure, unadulterated between subjects design couched within a within subjects design. So I can actually analyze my data like I would in a within subjects design, which is basically just average these two happy face scores together and average the happiness scores of the people that saw the sad face together and see if there's a difference between those two groups. Or I can ignore the second trial, acknowledge that it's adulterated by the first trial, and examine if I find the effect in the simple between subject study that is the first trial. The first one you see is pure, right? The first observation, the first trial in subjects design is pure. And if you set it up so that, it's counterbalance, that it's, people are randomly assigned to this first trial, that's a between subjects analysis just on these numbers right here in the first trial while deleting all the numbers in the second trial. So for me, right, the strongest case I can make, because some people don't like within subject studies for the carryover effects and all that other stuff. I can be like, well, I had the effect on the first trial, had a significant effect on the first trial, and I had the within subjects effect as well. So I think that is the best of both worlds when you're running a within subjects design is running a between subjects analysis on your first trial. So I hope that makes sense. So now we are basically done. And this is the problem set. This is your homework. The lecture's done. I've made my points. And I just need you to answer the following questions for your independent project design. If you have more than one dependent variable, choose your favorite. So your first question is provide a short narrative description of your study. In my study, I'm going to make it like yours. I manipulated race by showing participants people of different races expressing pain faces of equal intensity. All my participants saw all the faces. I measured gender with the following scale. I taught it was in there earlier. I'm measuring a lot of different genders. Participants get to choose. That's my other. That would be my independent variable, but this is a case where it's a measured independent variable. You see that? It's not manipulated, so that's why I don't call it independent and dependent all the time, because manipulations, right, aren't the only things that are independent variables. Measures, like in this case, can also be an independent variable depending on how I think about my study. And then I measured perceived intensity of the pain of the patient by having participants rate the pain intensity of each target they saw on a 1 to 10 excruciating pain scale. All I want for you is just to tell me a little bit about your study so I can learn about it. You cannot mess this up unless you don't tell me what your 2 IVs and your 1 DV are and how you basically measured them in a very, very short description, right? Then for each variable, I have 3 variables. I got to give it a name because I think that's good practice. So I have my race variable, I have my gender variable, and I have my perceived pain variable. Right? Is it independent or dependent? I'm not going to go through that, but for each variable, 2 of them are independent, one's dependent. For independent only, is it within or between? Well, my manipulation of race was within, right? Gender was between because it wasn't really a manipulation, but it's an independent variable. Is my variable discrete or continuous? Well, for my independent variables, both of them are discrete, right? My dependent variable is continuous. You're going to notice that's pretty much always the case. For discrete, is it nominal or ordinal? Well, they're both nominal, right? There's no like race, white or black in my experiment. There's no ranking there. It's just different people. And gender, the same thing, my different gender categories as well. There's no more gender, less gender. There's no more race, less race. It's just different categories. For continuous, is it interval or ratio? Right? So my continuous variable is pain intensity. There's no 0, so that is interval. And then I have to really analyze the variable in terms of, this is the hard part of the lecture, validity, power, and reliability. And then I want you to describe one predicted main effect in terms of cause. Not the interaction. I don't want to deal with that yet. Just one main effect. In my study, I can say my race manipulation caused changes in pain perception because I manipulated race and measured pain. If you measured for the gender one, I can't say cause. I could say gender's associated with perceptions of pain. If that were the case, it's probably not. Right? And then here's an example of me going through one of those examples for you. And now our lecture is done. Do the problem set, and that should be all great.